first thank the organizers, in particular Niloy, who got in touch with me and asked me if I could give a tutorial. And Niloy's brief was in particular to focus on the econophysics aspect of diffusion and networks. So I mentioned to Niloy that I wasn't quite aware whether econophysics has any special perspective on diffusion on networks, but I decided to also, apart from talking about biological epidemics, also talk a bit about social epidemics, in particular how innovation diffusion occurs and how physicists, for example, can try to model that. But what's the unifying theme of all these different things that I'm going to talk about? So I looked at the theme of the meeting, and I was trying to see how my talks kind of fit into the title. So I realized that I kind of touch, or I will try to touch upon all of these things, although it may not connect as well as I would like it to be, for example. So essentially, I'd start out by talking about epidemics, both biological as well as what I would call a social contagion, which of course have economic dimensions also. Towards the end of the first lecture, I'll talk a bit about what this has to do with behavior. So for example, behavior of agents when they realize that an epidemic is going on could actually affect, their behavioral changes could affect the course of the epidemic itself. I won't touch too much into this because this is very much work in progress still, but I'll just probably just point out what kind of results we are getting. So we'll briefly look into that. And what I would really like is in the second lecture to completely shift gears and go on to talk a bit about games, the concept of solution concepts in games, and in particular talk about a new and alternative solution concept, what we call the coaction concept. And while doing that, I will also talk a bit about this particular game, The Prisoner's Dilemma, which I hope would act as an introduction to the first talk after the lunch, which is going to be given by Shakti, who would talk in details about how this game played in a spatial context can give rise to many unintended or surprising consequences. So what's the relation between these different things? I mean, it's essentially the one language that would unite all of this is, of course, networks. And in particular, I will be focusing on modular networks. So in this way, it kind of builds upon what Chris has already been talking about. So yesterday, Chris essentially asked this question, what good is community detection for? So he was mentioning that, suppose you have, wonderful algorithms for detecting communities, but then if all that you're going to use for is just to say that, does it match with my ground truth, then essentially you haven't really learned anything new. So what I will be doing essentially is to try to answer this question, well, more like, what is the role of community structure on dynamics on networks? And the kind of dynamics that I'll be focusing in this particular lectures is that of epidemics, diffusion, social contagion spreading, and so on. Okay. All right, so with that very brief intro, let me get on to the main content of my talk. So much of what I'll be talking about, apart from the introductory stuff, is based on work done with Jason, who is in the audience, and also Chandrasekhar, who is also in the audience. And so if you have questions about this, please feel free to catch either of them after the talk. Before I get on to the specific kind of networks that I'll be talking about, let me just give you a very brief glimpse on the different kind of complex networks that we work on in our group at the Institute of Mathematical Sciences in Chennai. So essentially, we try to span the entire range of scale in which biological networks are seen, right from the intracellular level all the way to population and organ level. And of course, also at the species level, where we essentially look at how, for example, the structure of food webs affect the stability. So, for example, by looking at a food web, can you guess whether population fluctuations of a particular species is going to result in cascading perturbations which would eventually cause the entire food web to collapse. That obviously has implications for ecosystem stability. Surprisingly, it turns out that a lot of economists and social scientists have become very interested in the mathematical models describing food webs recently, because it turns out that there's a very a close parallel with the way banking networks, for example, the structure of banking networks affect their stability. So if you're interested in questions of systemic risk in economic systems, financial systems, then it turns out that studying food webs is a wonderful way of getting to grips with it. We also do a lot of work on neuronal network, how the structure of neural networks affect their functioning. So Shakti, for example, who will be speaking on this prisoner's dilemma on networks, also does a lot of work on this. So if you're interested about this, you could catch Shakti at some point and ask him for details on this. And we also do a lot of intracellular signaling, trying to see how networks affect the functioning of such intracellular signaling networks and so on. Okay, but in this talk, we'll be primarily focusing on this aspect, where we are looking at how, for example, population or the structure of contact networks in populations affect spreading processes. So of course, you can study epidemics at very different levels, starting from the most theoretically simplest, where you assume some kind of a homogeneous mixing. So you just assume that there are a large number of individuals. You don't care how many, let's say. You just assume that people kind of belong to different categories. Some people are susceptible to a particular infection. Some people are infected, and some people have recovered, and so therefore are neither susceptible to further infection nor are the fraction of population in each of these categories, and how do they change with time. So for example, models like the SIR, the susceptible infected recovered model, or various variants of it like SI model, SIRS model, SIS model, and so on, built upon such very simple assumptions. But then it can be a bit more ambitious, and you can say that, look, can I build in more details of society? So can I build in social structure? So here you are saying that not all individuals are same. So two individuals are not equally likely to get infected by a third individual, but it will depend upon what social strata they belong to, what age category they belong to. So for example, if you're a child going to school, you're much more likely to contract disease from your classmate or whatever. And then when you come home, you are likely to pass it on to your parent or not, depending upon the nature of the disease. So you should actually bring in these details of demographics into your model. So that's the first level of realism you can bring in. Another level of realism you can bring in is to introduce the concept of contact networks. So, if you were trying to model how, for example, a respiratory disease is going to spread in Bangalore, you could, of course, use a homogeneous mixing model like this, where essentially we will be treated at par with people who are resident at ICTS, and all of us will be treated at par with, let's say, people who are close to the Majestic bus terminus. But I think all of you know that if suddenly now a person who has a particularly virulent form of respiratory disease gets down at bus right now at the Majestic bus terminus, this person is more likely to infect people around that area rather than we who are kind of in an isolated part of the city. And because several of us would be essentially leaving the city within a few days, the people resident here would be much more likely than us to contract the disease later and so on. So therefore, it's important to take into account the nature of contacts that we have with each other when we are trying to figure out how a disease spreads from one person to another. And this is where the concept of contact networks come in. Of course, it's very hard to map out contact networks in general from individual to individual. So back in 2009, when the influenza H1N1 had its big outbreak in India, there was a kind of an initiative from the government to try to figure out how exactly the disease is going to spread through India. So I don't know whether you remember it, but the first reported case of H1N1 was this person who flew in from the US to Hyderabad airport, and essentially this person was caught at the airport itself and quarantined. And then people kind of got a bit wary that maybe we should put in lots of scanners at the airports and try to catch H1N1 infected people before they can get into the country and start mingling with the native population. But eventually, of course, it did break out, and it broke out simultaneously in several cities. There was an outbreak in Delhi, there was one in Bangalore, one in Hyderabad, and so on. But eventually, the biggest outbreak was actually in Pune, which doesn't have a big international airport or anything. So one of the questions that the public health agencies had was, why is it that Pune showed this, massive outbreak compared to the other metropolitan areas, which actually had the bigger airports, causing people to come from, which are the places where actually people flew in from all these H1N1 infected areas. So is there some way of figuring out why Pune, why not, let's say, Chennai, which actually has a major international airport? Chennai, in particular, turned out to be, spared from the worst of the epidemic. So these circles, small circles, represent individuals. Red circles essentially represent individuals who were confirmed to have SARS, whereas the white circles represent individuals who were suspected to have SARS, but they were never, their blood was never tested, and so we don't have confirmation that they actually did have SARS. Now, you notice that all of this is connected with these blue rhombuses or whatever, and these indicate the various hospitals that these individuals went to. Okay? So the thing that immediately jumps out from looking at this figure is that essentially SARS spread by people, infected people going to hospitals, passing on the infection to caregivers, doctors or nurses, who in turn, when they were looking at other patients, passed the disease on, and then these people, once they're discharged from the hospital, would carry the disease with them to their homes, and then the whole cycle starts anew. So this kind of network is, in a sense, what Chris is kind of referring to, because this is not direct contact network. Here you're talking just about people to play this kind of network. Yeah. Mm-hmm. Right. Yeah, fantastic point. Yeah, so as Chris points out, if you are just looking at this network, it's very hard to figure out whether it's just because these people were infected for independent reasons, and they just went to the hospital to get treated. So it turns out that they do have dynamic data. So this is just the what the composite picture, which is bringing together all the different data points that occurred at different times. But you could study it across time, and you could see, like, for example, how, for example, when a person was first infected with SARS, went to the hospital, then that generated further points. Basically, we know that it was the doctors and the nurses who got infected, who then passed the infection on to patients who were actually at the hospital at that time. So because of this knowledge, we actually can trace how SARS spread from person to hospital to person and so on. So by studying this kinds of networks, you could, for example, figure out that there are bottlenecks to epidemic spreading, which is probably where the most efficient controls can be put in. So if you decide to focus, filtering of individuals or trying to detect individuals who are probably infected with a particular disease and try to isolate them, maybe you should focus your efforts on these bottlenecks. So this led to a realization of the importance of tracing contact networks, tracing information about spatial locations of infected individuals to public health professionals, so much so that the CDC director of that time actually gave a talk which she called The Small Worlds of Public Health, in which she highlighted the importance of studying contact network structure for tackling major public health hazards. So what is this small world that is mentioned over there? So small world network, probably this has already been done in some of the lectures. Has it already been covered? No, okay. So the small world network concept, something which essentially emerged in 1998 in a very influential paper written by Duncan Watts and Steve Strogatz, in which they argued that neither regular spatial lattices, which physicists used to study as a surrogate for contact among nearest neighbors, nor the Edosh-Renyi type of random networks, which graph theorists studied a lot because of their theoretical simplicity, are very good descriptions of networks in real life. So if you look at social networks, if you look at biological networks, or if you look at technological networks like the internet or the World Wide Web, none of them are well described by these, either regular lattices or random graphs. Instead, they proposed another model, which for various reasons they call small world network. More about that in a minute. But the way they got to that is very interesting. So they said that, look, we know about regular networks, which are essentially just spatial lattices. And we know about random graphs, where you essentially just put, with some fixed probability, links between any pair of nodes. What you could do is you could try to interpolate from between the regular network and the random network and get a class of different networks, somewhat like this. You start with a regular network, and then you take a p fraction of the existing links, you break them, and then you randomly reconnect them to some randomly chosen node in the graph. So if p equals 0, of course you get back your regular network itself, but if you take each and every one of your existing connections and randomly reconnect them, then you get essentially a random network, which is the kind of graphs that graph theorists are very familiar with. But what happens if p is between 0 and 1? So you'd get something like this, where most of the links are still kind of what you had in the regular network. They are essentially connected. Each node is connected to its spatial nearest neighbor. However, there would be a few connections which would actually span across the lattice, so to say, and this might result in a change in the properties of this graph. In fact, when they looked at properties such as clustering and path length, they found that while the regular network has high clustering and large path length, the random network has low clustering and short path length. Small world networks, so to say, have clustering similar to that of regular network, but path lengths closer to what you see in random networks. So they have essentially a combination of high clustering and short path length. So why small world, first of all? So that's because Watts and Strogatz proposed that these kinds of networks can help explain the small world phenomenon, where the simplest way to think about it is just use a very commonly observed phenomenon. Whenever you are waiting at a station or at an airport, and you get bored enough to talk to your fellow passenger or the person who's waiting next to you, you start a conversation. At some point, you suddenly realize, more often than not, that you happen to indirectly know this person through some intermediary. So you suddenly find out that this person happens to know the boss at the previous company you worked in, or maybe this person is cousin of some friend you had in high school. Okay, and you say it's a small world. Okay, so the question is, how likely is it that in a planet with more than 1 billion individuals, you just happen to be next to a person with whom you share intermediary contact? So you could try to think about it in a very naive way. So you can try to do a back-of-the-envelope calculation like usually physicists do. So you could say that, okay, let's say roughly I know 100 individuals. And each of those 100 individuals know 100 other individuals. So in this way, how many maximum number of contacts do I know every person on Earth? So, assuming that the population of Earth is something like 10 to the power 12, it means that at just 6 levels of contact, you would know essentially 10 to the power 12 individuals. Okay? So here what you're doing is you are assuming that your contact structure, and again, this is harking back to what Chris was talking about in his lecture yesterday. So you essentially assume that your social contact network is like a tree. So you know like roughly 100 individuals. Each of them know 100 other individuals. So basically at first order of remove, you know these many individuals. They in turn know 100 each. So next remove, you know 100 to the power 3. So not surprisingly, at essentially at 6 degrees of separation, you know roughly the population of the planet. Okay? But of course, there's an enormous fallacy in this argument, and that's also something which Chris was kind of mentioning, which is that many of these individuals will, of course, know each other. So these contacts, which I just drew as a tree, are not really a tree, but rather they would form closed loops. And closed loops are very short lengths. Okay? So clearly, this kind of simplistic argument doesn't work. Nevertheless, the small world phenomena is, of course, happening all the time. So why is it that although our social contact network structure is not like a tree, nevertheless, it seems like it is? That, typically, whenever we meet a person, it would be easy to find, just a few intermediate contacts linking this person with me. Okay? And in a sense, the small world network model explains this. So it says that even though we might have most of our contacts arranged in some kind of a regular lattice where, typically to go from any point to any point would require an extremely long path length. So for example, here, to go from this vertex to this vertex, you essentially have to traverse to the entire lattice. But because of the existence of these few shortcuts, actually, for example, you can go from here to here using much fewer number of intermediary vertices than you would have required had your network been like this. So essentially, the lesson of the small world network is that even though our contact network structures have lots and lots of closed loops, the existence of a few shortcuts like that essentially makes it appear like a random network having extremely low path length, essentially which scales as log of the number of individuals in the network. All right. So in 1998, when this paper came out, it kind of revolutionized the field. I mean, overnight, complex network became, fashionable. Everybody started doing it. And people, of course, started finding small world networks everywhere. Okay? Not surprisingly, people in the mathematical epidemiology community also started looking at their models and were asking, maybe social networks are small world. And of course, if you characterize small world network just using clustering and path length, it's not surprising that you would actually categorize it as small world. So people started saying that, well, social networks are small world, so we should start looking at small world networks essentially to study how epidemics spread and so on. But then the question was, where is this small world pattern coming from? Fine, I mean, you can define a small world property as the coexistence of short path lengths and high clustering, but is this kind of network the only way to get it? Well, it turns out that modular networks or networks having community organization are also small world. So maybe the reason why social networks are manifesting all these small world characteristics is not because it looks like this, but rather it looks like this. And this is actually much more intuitive to understand, because we know that our social networks do happen to be clustered into lots of communities. Whenever you go to a party, this is like obviously manifest to us because we find people cluster into tight little cluster cliques where essentially everybody knows everybody, and they typically have very little interactions with people belonging to other communities and so on. So this idea that maybe small world property occurs in social networks because of their modular character is what's going to drive our foray into looking at the role of modular networks in modulating the course of spreading processes, in particular epidemics. So what is a modular network? So in short, whenever I can identify a subnetwork or subgraphs in the entire system such that there is a much higher connection density within these subgraphs compared to the average connection density over the entire system, I call this highly connected clusters modules. Okay? And a graph which has many of these modules, I would call a modular graph. Essentially, modules are a mesoscopic organization principle which lies in the regime in between the scale that is looked at by microscale structures like motifs, which essentially are interested in statistically significant patterns of connection between 2, 3, 4 nodes, and macro level properties like looking at clustering coefficient, average path length, which are basically statements about the overall network. Mesoscale properties, on the other hand, focus on properties which exist as a result of something which is happening due to relations between groups of nodes and the interrelations between these groups. So you could have essentially very similar microscale properties, very similar macroscale properties, but have two different networks in terms of their mesoscale properties. And of course, the dynamical processes that occur in such graphs would be extremely different. So then you'd be really puzzled because as far as the macroscale and the microscale properties are concerned, the two networks are essentially identical. But then, because of the different mesoscale properties, they manifest very different features. And so we'll be focusing on one particular mesoscale feature, namely the modularity. Now, what's the evidence for modularity of social networks? So there have been quite a few studies. One study in particular that we'll focus on is this one, which was done in 2007 by Jukka-Pekka Onela and his collaborators, which included Albert Laszlo Barbashi and others, where they essentially looked at the cell phone communication network of a major European nation, and they had access to information about who phoned who for how long, how many times, and so on. And on the basis of that, they could construct network which had links between pairs of individuals who had telephonic conversations. So of course, you could now introduce thresholds. You could say that, let's say I ignore people who had extremely short conversations with me. So presumably these were, telemarketers or something who just called me, and the moment they started saying, "Can I speak to," and misspelled your name or something, you immediately know who it is and you just switch off the phone, or some such thing. Or so you only focus on links which are in some sense socially relevant, and so therefore you could try to formulate such a network, and then they started the properties of such networks, and what they found was that if you look close enough into the network, you find the existence of communities with very strong interlinks, and these strongly connected communities have very weak connections which connect them to other communities. So typically you would have many frequent conversations between people belonging within one community, and conversations also typically of much longer durations than the conversations that happen between members belonging to two different communities. And other kinds of social networks have also been looked at, including that of scientific collaborators, that of email communication, web of trust, and even non-human animals, like dolphins and primates and so on, all of which show evidence of modular organization, or that fact that you could always find very strong communities where within each community you have very strong amount of communication, and between communities you have weak communication. So one such wonderful data set that was recently made available to us was information about the actual social contacts between individuals of 75 different villages in southern Karnataka. So this information was collected by an institution which was interested to see whether microfinance kind of initiatives would be successful in such villages. So since microfinance is reputed to depend, the success of microfinance is reputed to depend very much on the social relations that exist within a community. So therefore, they thought it was very important to collect information about, who is friends to who goes to the same temple, who, goes to which shop and, has regular conversations with which shopkeeper and so on. So there was a very detailed questionnaire that, they had, and they went and collected this data from these different villages. And most of these villages were small, but, a few of these villages had, more than 1,000 different individuals. So for example, one such village, which is identified by this anonymization tag 55, essentially had close to 1,200 individuals, of which we are showing only the largest connected component here, which essentially has these many individuals. And what we did was we tried to find the different communities, so to say, or the different modules of individuals who have much more intimate contact or intense contact with each other than with other members of the village. So there are, of course, many ways in which you can try to find communities. So for example, you could use the Q measure, which was proposed by Newman in 2004. Essentially, it asks how likely is it that the connection that I see happened by pure chance. So essentially, you know how many connections the ith individual has and how many connections the jth individual has. And on the basis of that, you estimate the probability that they're connected, and you compare it with the actual occurrence probability of such links, and you try to guess the communities and try to see whether this maximizes this measure given this probability of actually forming a link and the actual frequency of such links. So of course the problem is that we don't have a assured way of finding the partitions which would maximize this value of Q. In most cases, what we do is we use various kinds of optimization techniques to come up with the partitions which would have almost a maximum value of Q, but we have no way of assuring ourselves that that is indeed the maximum. So in this particular graph, what we have used is this spin glass simulated annealing method, which was proposed by Reichardt and Bornholt in 2006. But you can try to assure yourself that this is not very far off from modules that you will detect by using other methods. So in fact, we also used at other times spectral methods and other kinds of weighted community detection algorithms and so on, which give qualitatively similar results to what we show here. In any case, what you notice is that there are quite a few modules, in fact, 25 different modules in this particular population. And what you might be interested to ask is, like, for example, if there's an outbreak of an epidemic in this particular network, how would the fact that it has this particular community organization affect how the epidemic spreads and then the eventual fate of the epidemic? Yeah. Mm-hmm. Okay, I'm not particularly knowledgeable about microfinance, but the way I understand it is, microfinance is all about giving loans, and you don't have a surefire way of ensuring that the people will actually pay you back. Okay, so the idea is that if you can have enough social cohesiveness in a group, so that there's kind of a social pressure, a peer pressure, if you like, that you took the money and others are paying back, so you should also pay back. So therefore, if you have high social cohesiveness in a particular community, it's much easier to recoup your money than in in places where people are much more anonymous. So, like for example, in typical urban situations where you don't know others from Adam, you are likely to say that, okay, so I took the money, so what? Nobody will know. Okay? Whereas in villages where everybody knows everybody, so to say, you have some kind of a fear of a stigma associated with you that you took the money and you never paid it back. Also, there's that much more social support in a village to ensure that your initiative succeeds. So, let's say you invest in a sewing machine, you still have to figure out people, who would give you the raw materials and, people who will market it for you and so on. So if you're already part of a, very well-connected social network, you're much more likely to, ensure that the initiative that you're part of will succeed. So, you find out a person who is willing to take your products to the city and market them for you and so on. So this, I guess, is the reason why people are so interested in figuring out social networks in connection with microfinance. No, so this is one particular village. Each node is an individual. Yeah. This is just one village. As I said, it's village 55, which has and this is like 1,151 individuals. And these contacts essentially, so this is actually a superposition of the different types of contacts that they had information about. So typically this questionnaire would have detailed information on different types of contacts. So there would be information about family relations. So, you are friends, brother, sister, father, mother of this individual. They have information about friendships. So you know that this person is friends to this person. You would have commercial relations. So, which shop do you go to? So who's the shopkeeper there? And then they would have religious relations. So which temple do you go to pray? Or which mosque do you go for your namaz? And so on. So they would have like 12 different categories of links. So what we did was we essentially condensed all of those links into one giant network. But of course, you could decide to study each of these networks separately, which would turn out to be even more fragmented. Any other questions? Yeah. Exactly. Right, precisely. So in fact, this 2007 work by Onella et al. That I referred to, the title of the paper actually refers to Granowitha's work. So essentially, they claim that they have found evidence to support Granowitha's hypothesis of the strength of weak ties. So essentially what happens is that in your own community, you would have very strong links, but since the information available to you is essentially same as the people in your community, you're very unlikely to get novel information as such. So most of the time, the novel information actually comes from this intermittent links that you have with other communities, and that's what gives rise to the strength of these weak ties. The weight, yeah, so essentially the proxy for the weight is either the frequency of telephonic contact or the total duration of telephonic conversations that you have with different individuals. So that's the proxy for the connection weight. All right, so the particular thing that we were interested in was the long-term fate of the disease. So, there have been a lot of work done on the initial phase of an epidemic. So at the time it breaks out, how does it flow and so on, and how does the existence of modules affect the probability of success that the epidemic would actually break out in such a network. But not too much work has been done on what happens after an epidemic has started. So for example, typically you would expect that once an epidemic starts, you'd have essentially an exponential growth phase when the infection essentially finds virgin territory. Everybody is fresh meat, so to say, right? So the virus or the bacteria just goes and colonizes each of these individuals and spreads from person to person. But after some time, this supply of fresh meat dries out, right? So most of the individuals this pathogen encounters have already had the disease, okay, and have recovered from it. So then it tries very hard to find susceptible individuals, and eventually at some point, it's no longer able to find fresh susceptible individuals, so it dies out, okay? Or does it? Okay, and this is a million-dollar question in public health, because it turns out that you could, depending upon circumstances, either have the contagion completely, or have the epidemic completely die out, and you declare the epidemic at an end, or it can actually become endemic. Okay. It can stay at low intensities in the population for some time, waiting for susceptible individuals to increase in numbers, which could happen in multiple ways. Either, at very long terms, of course, people who had earlier recovered from the disease will eventually die and be replaced by a new generation of individuals who don't have resistance to that disease. Or you could actually have diseases where you eventually lose immunity after time. So for example, syphilis is one very well-known disease where people actually lose immunity after long times. Or you could actually have a turnover in the population where people who were exposed to the disease and had resistance to it move out to other locations. Migrants from other areas who were never exposed to the disease come into this new area. And so therefore, suddenly, you have a fresh batch of individuals who are susceptible to the disease. Or sometimes the pathogen can itself evolve a bit. Okay? And this happens, for example, for flu virus, where you have a high degree of mutation. And so therefore, even though you had caught flu this year, it does not give any guarantees that you will not be susceptible to the flu virus next year. So the long and short of it is that there are many mechanisms by which people can become susceptible, or even the population can again gradually gain its susceptibility over time. And so the question is, are there certain kinds of network structure which is more likely to promote the persistence of the disease than other kinds of network structures? So in particular, we are looking at persistence probability. That is, what is the probability that the disease will circulate in the population for an indefinite period? Yeah. Well, that's, I'm sure, yeah. Correct. Yeah. Well, that's a hard one to answer. Sorry? No, I think Chris's point is that the basic production number of the disease AIDS is actually extremely low. So, if people were extremely long-lived, then of course, eventually you would expect that sooner or later I will encounter such an individual. But, people die, and, even though you have AIDS, you're not going to keep passing on the disease forever. Yeah. Yes, that's true. No, but, presumably, once you are aware that you have AIDS, you will also have, corresponding changes in your behavior. There will be change in the response of the society to AIDS. So for example, this is quite well known. When AIDS first became very well known, people started shunning contact with, everybody who was known to have AIDS. So this also could have had a bearing. But if, there could be multiple number of reasons, and I'm sure some of that might have been modeled. But one could think of many ways in which this global prevention could have been, curtailed at some point. So anyway, the kind of model that one could use for looking at this long-term persistence of such an infection is based upon this so-called SIRS dynamics, susceptible, infected, recovered, susceptible. I'm sure Ganesh has covered already the SIR model, so I won't go into the details of this. Just suffice to say that at the most basic level, you can think of individuals as belonging to 3 different categories: susceptible, infected, or recovered. And there are different rates with which you go from susceptible to infected. So for example, if a susceptible individual meets an infected individual, then with some probability the susceptible becomes infected. And then once you're infected, with some rate, you become recovered, which is the rate is actually reciprocal of the average infectious period. And then with some rate, you actually lose that immunity and become susceptible again. Again, let's say this rate is reciprocal to the average period over which you have immunity to that particular contagion. So one of the most important parameters associated with epidemics is this basic reproduction number, which essentially is quantified saying what's the mean number of new infections which are caused by a single infected individual in a wholly susceptible population. So the idea is that, let's say you have, on day 0, this particular infected individual, and then you are basically trying to trace how many other individuals typically would that primary infected person leave as a result of this infection. So on day 1, essentially this person has infected 2 individuals, and then you trace how the secondary infections go on after this. So for example, you ask how many infections on day 2 does this particular infected individuals result in. So this infected individual infects 1 more. This infected individual does not infect any other individuals. And so therefore, essentially the chain dies out here. So whenever a chain dies out, essentially you color it black. So you can see that in this way, you can try to trace how many secondary infections occur as a result of a primary infection. So every time, at every point on this particular tree, you can ask, okay, from one particular node, how many other nodes branch out? So the average number of that branching is what is known as the basic production number. And not surprisingly, epidemic happens only if this number is greater than 1. You need to have more than 1 individual on average who would get infected by you for the epidemic to continue and spread through society. Now, if you are studying it in the context of a network where you have n individuals and you have all these rates, it's not very hard to show that essentially it's at some approximation just the product of the total number of individuals, the rate of the infection, alpha, and the duration of the infection, tau I. So if this product is greater than 1, then essentially you have an epidemic. So the next thing we did was we did a lot of numerical simulations on the social network data that was available to us. So these simulations are all stochastic and so happen to be based upon the very fundamental Gillespie algorithm, one of the most fundamental algorithms for looking at stochastic processes. I won't go through the details of this, but Chandrasekhar is in the audience, so if any of you are curious about this algorithm, you can always ask him later on. Suffice it to say that essentially you evaluate the probability of, let's say, an infection event happening, a recovery event happening, and again, a recovery individual becoming susceptible event happening. So you evaluate this from the ratios of the individual rates to the sum of all the rates. You also find out the time at which the next event is going to happen based upon the probabilities. And you use these probabilities to essentially update the network again and again as you essentially find out which individual, you basically declare some individual to become infected, some other individual to become recovered, and so on. The only point of interest to note here is that unlike the usual Gillespie algorithm, where you take the rates to be constant, here the rates are actually time dependent, and that's because in the usual Gillespie algorithm, if you look at the average duration of, let's say, infection, you find that that follows an exponential distribution. However, in real epidemics, if you ask what is the typical duration over which individuals are infected with an infection, you find that that follows a very narrowly distributed distribution around the mean value, okay? Whereas Gillespie would give you something which looks like this. So in order to make sure that we got a distribution like this, we had to actually take rates which are time dependent. All right, so just to show you a few snapshots of the simulations. So this is, let's say, at the very beginning of a simulation. So in the social network, we have labeled individuals who are susceptible as blue nodes and individuals who are infected as red nodes. So this is already after the infection has started. So you can see quite a few nodes which have already become infected. So if you follow along, you find that after some point, you have some people who have now recovered. And presumably some of those recovered individuals have become susceptible again. So you can follow along over time, and you can find that with time, people are becoming infected, then they recover, then they become susceptible again, and so on. So now you can ask, how does the structure of the network affect the long-term fate of this epidemic? So one of the first things we notice is that if you look at the empirical network, highly infectious diseases, which have very large basic production numbers, something close to 7. Okay? So that essentially means that on average, each primary infected case is infected almost 7 other individuals. You find that the infection is persisting for almost as long as you care to carry on the simulation. However, if you look at the corresponding randomized network, and this is not a random network, but essentially what you do is you take the original network, you preserve the degree sequence. So you ensure that every individual who had 10 contacts continues to have 10 contacts. You just randomize who these contacts now go to. Okay? So what you have done is that keeping the degree sequence intact, you have just destroyed the community organization of the network. So by doing that, essentially you find that such highly infectious diseases or epidemics actually quickly die out. So this is a fairly surprising feature of community organization, that even though these highly infectious diseases persisting for extremely long times in the empirical network, they quickly die out in a corresponding randomized network. And if you decide to actually selectively eliminate the intermodular contacts, this effect is even more pronounced, which assures you that actually this is related to the modular structure of the population. To assure yourself even further, what you could do is, you could ask, what is the probability that the epidemic will persist for longer than the simulation period as a function of the basic production number for the empirical network and for the corresponding randomized network? So here you find that for epidemics with R0 greater than, let's say, 2 to something around 12, you have finite probability that the epidemic is going to persist for extremely long times. Now, for the corresponding randomized networks, you find that, of course, you still have epidemics with R0, let's say, between 1.5 and, say, about 6, for which the epidemics stay on for very long times. But the range of R0 for which you see such persistence is actually shifted to much lower values of R0, or, in other words, for lower infectious or epidemics with less infectiousness. So you can characterize the difference between these two distributions by some metrics. So for example, you can use Jensen-Shannon divergence, which is a well-known measure to quantify what's the difference between two distributions. And you could show how this varies as a function of the modularity of the 75 social networks which you're studying. Okay? And what you find is that almost an exact linear relationship between the modularity and the difference in behavior between the empirical contact network and the randomized contact network, which shows you that modularity is in fact playing this key role in ensuring that the epidemic persists for very long times. In other words, having community organization results in extremely long-lived epidemics. Now, why? So this has to do with understanding the diffusion process on modular networks, and what I'll do is I'll stop at this point and have this break, and we'll continue on the next one.